So in this case we have the example of a guy riding a roller coaster, so you should pause this, write this down, try to do it yourself. But now it's about normal forces and not tension like the rubber stopper example. Let's look at an animation really quick. And in this animation, I'm going to go slowly through it. What you can see is that the car will go through the loop, and the normal force, the red is the weight, the yellow is the normal force. The normal force decreases down to nothing in this video. Then at the bottom of the loop it really increases. Then when it goes on a straight path, the normal force just equals the weight. So the normal force changes throughout this path. And in particular, what I want to point out is that at the top it decreases. Now the unfortunate aspect of this animation, and I'll just try to control this with the slider. The unfortunate aspect of this animation is that at the top it does not show a normal force, and in this problem there is a normal force. I just want to point out that it's less at the top than it is at the bottom. As you can see, at the bottom there's a large normal force. So it's just like, now that's exaggerated, but this is just like the rubber stopper. And again, I wish that it would show a normal force at the top, but they wanted to show you the minimum speed it could go and still make the loop. So I'm going to draw my forces at the top and at the bottom. I'm going to draw a circle. I'm just going to draw a circle, and I'm going to do both on this one circle. So at the top you have weight down and you have a normal force down. So I'm going to label this force W for force weight. I'm going to label this Fn for force normal. I don't know which is greater, I'm not really concerned at the top. Now at the bottom I know that the normal force is greater than the weight. So this is, again, these are normal forces because they're being supplied by the surface of the track, as opposed to the case of the rubber stopper where it was tension that was acting on it. Now what is the normal force on him at the top of the loop? The first thing I'm going to figure out is, I think you'd probably prefer to do it this way, is you can write down F net, which is F sub c, ignore the bell, it's the end of the day. That's mv squared over r. And I'm not going to bother going through, I'm just going to say we know the mass. I'm not going to bother writing out all the calculations for you. I'm just going to say we know the mass, we know the speed, and we know the radius. So we can calculate that value. I'm going to pause it while I go calculate a number for that. Just going to try to pause that. And the value I'm getting on my calculator for that is 1,203 newtons. And again, that's a net force. That's just the total force that I need. And I know that these two values, these two have to add up to that net force, which is the total value that I need. So I'm going to simply write down that I know that the force normal plus the force weight, which is just mg, has to equal F net. Okay, and the force weight, you do mg and you get 710. So you think about that and do the math. But as you do the math, you realize that the force normal, and this will be our answer, has to be 493 newtons. Again, you can think about the equations, but don't freak out about these equations. This right here, people get really intimidated by that. All that is saying is that if you look at this total force that is necessary to keep the object moving in a circle, these two have to equal the total force that's necessary to make the object move in a circle. So that was part A. Part B. Part B, this is just like the rubber stopper, but now it's a normal force. Now I've got competing forces. So this normal force is competing with this weight. So obviously the normal force has to be really big, but if I just write down an expression for it, it's force normal minus the 710 for the weight has to equal the 1203, because again, we always need those to equal the 1203. So then the normal force that I get, I'll add that really quick, 1203 plus 710 is 1,913 newtons, which is a greater force at the bottom of the loop than at the top of the loop, like we expected from the animation.